function is basically objective function is linear one. So the level curves are basically the linear one. So here your linear, this is your linear function. So your uh, objective function are basically the linear hyperplanes, and that objective functions are these are your level curves. Okay, so these are your level curves of solving that type of linear programming problem. So here the objective function is C transpose X, that is linear. So its level curves are hyperplanes, and that are orthogonal to that this dotted line. Okay, to this vector, this linear function that is C. Okay, so the point is here we can find any point. That point is, suppose that is your x star, and that is your optimal solution of this linear programming problem. And here the direction of this is the perpendicular of that, and the direction of minus C. Okay, and this angle is 90 degrees. Okay, so this is usually you have already done in your linear programming problem. So okay, so here we discuss about what are the types of linear programming problem here. Okay, and here we go to the main problem, that is your geometric programming problem. Before that, some special types of linear programming is already there. First one is linear optimization problem. You know that here when objective function and equality constant are all are linear one, or you say that all are affine function, then this type of programming is categorized into the linear programming problem. And next one is a linear fractional programming. Okay, so this is a fractional programming, and here in this case, this is a problem to minimize a ratio of affine functions, okay, over a feasible region, and that feasible region is polyhedron. So the problem is
सर डायग्राम को प्लीज एक फिर से एक्सप्लेन कर दीजिए.
okay. So in basically in linear programming problem, you find the feasible region, and that feasible region comes from this inequality constants and inequality constants. Okay, so here you find this is your feasible region, and in that sense, here this P polyhedron, that is your feasible region. Okay, and your level objective function is basically the linear function. Okay, and that linear function, this means your level curves are linear one. Okay, so here okay, so here we can write that here. So here the objective function, that is C transpose X, and that objective function is linear. So its level curves are basically, in dimension you find this level curves are hyperplanes, and that hyperplanes are orthogonal to this vector. In hyperplane, you know that this is a vector that is orthogonal to vector C. Basically, that vector is orthogonal to vector C because this is C transpose X. Okay, and here usually you denoted this hyperplanes by dotted line. Okay. So you define that is dotted lines, and point X star, the point X star is optimal solution. This is optimal, and it is the point uh, in your polyhedron, that is P, as for as possible possible in direction, because this is a problem of minimization in the direction of that minus c direction. Okay, so this is the direction of c, and here the direction is hyperplane direction is vector. This is plus c, and this is minus c. So you have to find the minimized of that program. You have to find as or as your minimum value. Okay, so this is a general form of linear is a quadratic programming problem. So your level curves are be in nature of this parabola type. This is a quadratic function, and you have to find that axis term. Okay, so here the next one is a linear programming problem, a linear functional programming problem, and in this case, your is minimizing a ratio of affine functions or linear functions over the feasible region, and that is over a polyhedron 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 is called a linear fractional problem. Okay, so here basically in this type of problem you have to minimize your objective function, and subject to the constraints are same like linear programming problem, but only one difference is that your objective function here, this is your affine function, but here your objective function is here your objective function, that is f naught x. This is c linear function, which is c transpose x over t, or some another dimension. Suppose if we write e transpose x plus transpose f. So this type of fractional, and both are the linear functions. Okay, so here the objective function is basically here the objective function. The objective function is quasi-convex basically. So this is quasi-convex. Okay, so in fact this type of quasi-convex function are usually we say a function is quasi-linear function, which is okay. So is so this type of linear programming problem is categorized into the linear fraction programming problem. Okay, so here this type of program is known as basically quasi-convex optimization problem. So we also know this linear fractional programs are quasi-linear optimization, because our main objective function, so this type of problem is known as. Okay, so next one is quadratic optimization problem. Okay, so here was we only discussed what type of programming problem and what are the basic difference between these two programs. if the inequality constants and equality constants are both are defined in both cases, and if the objective function is purely linear or affine, then this is a linear problem. And if this objective function is quasi-linear function, then it's a quasi-linear optimization problem. So in next page, we the quadratic optimization problem. And in quadratic optimization problem, just both condition are remain same. If, this subject to the constants are remain same. This inequality constants are always affine functions. Okay, but if are affine, this is linear programming problem. The objective function is linear, so you know that this is linear problem. Okay, or you say that this is a quasi-linear problem. If objective function is our quadratic function, then the program is categorized into quadratic optimization program. So next page is quadratic optimization problem. Okay, so here if we write minimize the function and this objective function and subject to constants are, say, gx is less or equals to h and ax equals to b, this type of your functions, and these functions are affine, and this is convex function. So if this means both are linear functions, and your objective function is here, this objective function is the quadratic form. So if we write this is in the form of x transpose px plus q transpose x plus any constant r. Okay, so where this p is belonging to the symmetric matrix, this is Sn plus, this is element of that, and your G be any R cross matrix, this is a cross n matrix, and here the number of if there are n number of inequality constants and p number of equality constant. So this is a matrix of order p cross n, because n there is a x with a vector dimension Rn. This means this is G with the matrix of m cross n and A with the matrix of p cross n. This type of programming is known as the quadratic program. Okay, so here your constants are basically your objective function. This objective function is uh, a post-convex. This objective function is this thing, and your inequality constants are affine. Okay, so here your inequality constants are affine functions. So in quadratic program, we minimize a convex quadratic function over a certain region, and that region comes from a polyhedron. So if we take this type of visible region of your polyhedron, okay, suppose this is your inequality and inequality constants. Okay, and here your objective function is quadratic. So here your level are basically the quadratic one. So you in this case your sets are supposed like that. These are the quadratic functions f naught x. Okay, so you have to find the feasible optimal solution, that is x up, which is in the direction of, this is minus direction orient of your objective function, that is f naught x. Okay, so here you can find your दिस वैल्यू। ओके, तो इस पर हम न्यूमेरिकल हम करके दिखाएंगे क्या है, ये भी कल हम इस पे सिर्फ आपको बता रहे हैं कि ये इस तरह की चीजें हैं। ओके, न्यूमेरिकल जब करेंगे तो इस क्लियर होगी ये चीजें क्या है। Okay. So here, your objective function, the f naught x and your x star be the optimal point. Okay. These are basically some different types of optimization problem. So basically, our main goal is to discuss geometric. So in our your course, this programming is given, that is geometric programming. And all are linear and other quadratic programming, integer programming, you've already studied in your graduation level. Okay, so here the main programming is geometric programming. So what is geometric action problem? So we can write an optimization problem of the form minimize objective function, minimize your f naught x, that is objective function, set the constants subject to constants. Constants are given by some different functions, that is our m functions, fx, that is always less or equals to 1 when I is 1 to m, and there are some equality constant, that is hj of x, that equals to 1. This j varies from 1 to p. So these are m number of inequality and p number of equality constants. And here, one thing is remember that your of function, that is f naught x, and your inequality constants f1, f2, up to fm, all are all are here for geometric programming. For geometric programming, objective function and inequality constants functions all are polynomials. All are polynomials, and your equality constants, that is up to there are p number of equality constants that are monomials. Okay, so this type of optimization problem is known as is called is called geometric programming. It's called geometric. Okay, and here your domain of this problem, the domain of this problem is usually defined by D, and that is positive definitely. So, okay, and the constant is x is always greater than 0. Okay, the domain is your Rn plus plus. Okay, of course x is greater than 0. Okay. So this is so what are the definition of polynomials and what are the definition of this monomials? Okay, so in next page we define what is polynomial and uh, monomials. So next page, function is defined from Rn to R with domain domain is domain of that function f, that is Rn plus. This is defined as this fxn. This is c and x has component x1, x2 up to xn. X1 to the power a, x2 to the power some another, x3 to the power some another constants a3 up to xn to the power m. Okay. So this type of function where your c is arbitrary greater than zero, strictly greater than zero. Okay. And this is called monomial function, or simply you say that monomials. Okay, and second is polynomial. So a sum of monomials that is you can write a function of the form, a function of the form that is fx summation over suppose k equals to 1 to k ck x1 to the power a1k, x2 a2k, x3 a k up to xn a and k. So if this type of there are k number of terms, okay, there are k terms. So this is the form here. In all monomials, there are C1 go to ck. All ck is strictly greater than zero, which is a sum of monomials. So that's why this is greater than zero. Okay. So this is called polynomials function uh, with k terms. Simply polynomials. Simply polynomials. Okay, so one main property of this monomials and polynomials is that uh, this product of we take polynomials and product of monomials. Okay, so what is the result of that? Okay, if p is for polynomials and m stands for, okay, so if we product of these two functions, polynomial function and monomial function, the resultant is polynomials. Okay. Similarly, uh, if we take polynomials over monomials, so result always polynomials. Okay. So here, the main property of polynomial is closed. This is closed under this addition operation and multiplication of order. Okay, so polynomial, if we addition of two polynomials, it's also a polynomial, and for these two polynomial is also polynomial, and your monomial is closed
सर वो
under
पी बाई एम के पहले जो सिंबल यूज किया है क्या है सर, नहीं समझ आ रहा.
this. Similarly लिख रहा हूँ मैं actually. This is similarly
ओके
p over
ओके
m
सर.
that equals to p. This polynomial is closed under addition and multiplication of one, and monomials is closed under multiplication and division operation. Okay, so these are the basic properties of here polynomial and monomials, because we define here that we deal the problem of geometric programming problem, and where our objective function, quality functions are always polynomials, and our quality constants function are always monomials. That's why we define what is the definition of polynomial and monomial, and what is the some properties of this polynomial. Okay, so now where main concern is that if we write problem of geometric problem, and we try to see that geometric program are not in general a convex optimization problem, but can be transformed to convex programming problem, change of variables and transformation of objective and constant functions. Okay, so in next page, if we take an example of geometric programming problem. Okay, so next page. So, so if you consider the problem, suppose if we have a problem of maximize, not minimize, we have a problem maximize, suppose x upon y, and we take subject to the constants, small small optimization problem subject to the constants, and constants are suppose 2 less or equals to x less or equals to 3, and suppose x square plus 3y over z, this is less or equals to root y, and say x over y equals to z square. Okay, so this type of problem here, look here, this is a x over y, this is linear over linear, so this linear type of function, but here your all equality constants are non-linear one. If suppose if all are linear functions, and this is a quasi-linear function, then this optimization problem is reduced to the linear fraction optimization problem, or you say that quasi-linear optimization problem. But here, this problem is not linear, but this is a quasi-linear function. But here, these all are not in the linear function. Okay, so that's why this is not categorized into the all one problem which we had already discussed. Uh, so therefore, you have to reduce this optimization problem in the special case of honest optimization problem is your geometry programming problem. Okay, so here your variable here this is given with what is your variable x y z. So these all are real one. Okay, variables with variables x y z is belonging to the real R. Okay, and if you using this here, this is your implicit function. This is also your implicit function of x y z. Okay, so your constants are x y z are greater than 0. Okay, so if we use some transformation and we obtain the equivalent of this programming problem. Okay, so here our in geometric programming problem. Our problem is minimization problem. Okay, so here maximization of x by z, x by z, x by y. So this problem that is maximization of x by y, same as minimization problem of y over x. Okay, so this means the right maximization problem x over y is same as minimization problem of y by x. Okay, so y by x are you write this problem is minimization problem of this x to the power minus 1 y, because we can write here y over x is x to the power minus 1 and y. Okay, and subject to the constants and constant here 2 is lesser equals to x lesser equals to 3. So here we can write this 2 over x is lesser to 1 from these two inequality, and here this inequality you can find x 3 is lesser equals to 1. Okay, from this you find this thing, this 2 you can find this inequality. Okay, so this inequality you can write here 2x to the power minus 1 is lesser equal to 1. And here this problem is written as 1 by 3 of x, this is lesser equals to 1. So we can write in this form of monomial sum. Okay, and next one is x square plus 3y by z, this is lesser equals to root of y. Okay, so if we dividing by this y to the power half to both sides, this equals to x y to the power minus half plus 3y to the power this y and root y, so this becomes square root of half, and z denominator term, so this z to the power minus 1, this is lesser equals to rewrite this inequality constant in this form. Okay, so this is your first inequality, this is your second one, and this third one inequality constant, that is x over y, this equals to z square. And if we're dividing by z square, this becomes x y to the power minus 1, z power minus 2, that equals to 1. Okay, so look here, your inequality constant, some x, y, z to the power some real number and multiplied by here your ck, and ck here this is 1, here 3, this is greater than 0. Okay, so this is your polynomial, because this is your monomial, this is your monomial, and sum of two monomial, this is your polynomial, and that is lesser equal. Okay, and this is simply equality constant, and equality constant we know that in equality constant only one monomial is here. So this is some x to the power y to the power and z to the power, multiply here some c, and that's equals to here 1. Okay, so this is your monomial. So you can find this is your monomial, and inequality constant this one and these two. Okay, so these are your monomial of course monomials. Okay, so your polynomial is also your monomials is also belongs to all monomials are polynomials. Okay, so you write this program in similar manner by using some transformation. So using the simple transformation, we obtain the equivalent standard form of geometric program, that is minimize, and that objective function is x inverse y. The constants are 2x minus 1, which is lesser equals to 1, 1 by 3 x, this is lesser equals to 1, and x square plus y to the power minus x square y to the power minus half, x square y to the power minus half plus 3y or half z minus, this is less than equals to 1, and x y minus 1 z to the power minus 2 that equals to 1. So if we compare your standard of this geometric programming problem, so your this problem is this to geometric problem. Okay. So you can rewrite this problem in your standard form of geometric programming problem. Okay. So this is a simple example of geometric programming problem. Okay. So now main thing is that we have to prove that this your convex optimization problem. So in next page, you can write your geometric program in convex optimization problem. So geometric program in convex form. So basically, your geometric programs are in general convex optimization program optimization problem, but they can be transformed to convex optimization problem. Okay. So by changing some variables and transformation of objective and constant function. Okay. So problems by change of variable, change of variables and transformations of the objective function and constant functions. Okay, so if we assume that suppose f is to monomial function of x and defined as fx is some constant x1 to the power a1, x2 to the power a2, where a1, a2, and an are variable. Okay, so if we use some variable here, so here we will use the variables which is defined as suppose yi, and all yi, y1, y2, y3 is logarithmic of xi. If you take this type of size, you can write in short, xi is basically exponential of yi. Means x1 is e to the power y1, x2 is e to the power y2, and so on. Okay. So then by change of variable, if we change this variable, so then by change of variables, your fx function is originally defined as x is n dimensions. So here x is x1, x2 to the xn component, and this is now a function of all x is e to the power y1, y2 in such manner. So this becomes e to the power y1, e to the power y2. Okay, and e to the power. Uh-huh.
ये जो आपने लिखा हुआ है हेयर, ये उसके बाद क्या लिखा है?
Here we will use here
Okay.
we will use the variables defined as yi that equals to log of xi. So if we define this variable y1, y2 to yn like this, so all xi equals to exponential of yi. So here your function monomials basically fx. If your function is x1, x2 up to xn, your function is now the variable is changed, and here y1, y2 up to yn. Okay, and here your function is defined by the formula. So this equals to c first one to the power a1. So this means e to the power y1 to the power e into e to the power y2 to the power a2 e to the power y3 to the power 3, and here e to the power yn to the power an. Okay, and now if we multiply here, so you get here c multiplied by e to the power. This is a1 y1 a2 y2 a3 y3 to sum of this an yn. Okay. So now this can be written as this c can be written as exponential of log c. Okay, so you can write this c is e to the power log c. Okay, and multiply by this e to the power here a1 a2 a3 a2 a. So this is a vector. So this becomes a transpose. This means this is a vector with y, and y is the this thing. Okay, so you can write a transpose of y. So this becomes a1 y1 a2 y2 to an yn, and exponential of 2 is equals to this equals to, you can write e to the power a transpose y plus log of c, because exponential of this product of this. And if we take log of c, because log of c with any velocity is greater than 0, and this is here you know that this c is greater than 0. So here c is greater than 0, logarithm of that is another constant. Suppose that constant is b, because the c is the arbitrary constant, so that's why this is a b. So this equals to, you can write e to the power transpose y plus b. Okay, so now here by using change of variable, you find this monomial function into the exponential of this linear function, that is your affine function. Okay. So by using that transformation, you find the exponential of affine function of your main monomial function. Okay, so here you write the change of variables that is y, and that yi is log of xi. This turns from monomial function, monomial function into the exponential of an affine function. Okay, so similarly, if a polynomial, so on next page, similarly, if f is polynomial that is to fx this equals to summation of k c x1 to the power a1k x to the power a2k up to xn to the power a and k. This is your that. Then by using that transformation, you can find your fx is summation of k equals to 1 to k exponential of ak transpose y plus bk. Okay, so for all individual, and each monomial is exponential of this affine function, and if its summation is equals to summation of exponential of all these monomials. Okay, so here what is the value of ak is a1k k up to ank. Okay, so now and what is bk? Bk is arbitrary log c1 for first one, log c2, log c3, log c4. This is log of ck for any general bk. Okay, so after the change of variable, so after the change of variables, your polynomial becomes sum of exponential of affine function, exponentials of affine function. Okay. This means your after this change of variable, your monomials are exponential of affine function and polynomials are sum of exponential of affine functions. Okay, use and write this geometric program in this new variable, then the geometric program this can be expressed new variable, that is y, new variables, that is y, as the problem is minimize objective function. The objective function is polynomial. So here this f naught, so this we can write here k naught in the form of this some exponential function, which is a0k transpose y plus d0k. Okay, so polynomial, which is the sum of your exponential of prime function, and subject to the constants, of first inequality constant, that is also polynomial, and that polynomial is there are m number of polynomials. So this here k equals to 1 to suppose ki and I equals to m. So this is exponential of k transpose y plus bik. This is less or equals to 1. Okay, because this polynomial can be written in the new variable form of y, and here your I varies from 1 to m, and your inequality constant, that is your modes, and you know that monomial is written as exponential of your affine function. So we can say g j transpose of y plus any hj that equals to 1, there are p number of inequality constants. Okay, so here this is your aik. Basically, aik is your element of Rn, and here even from this objective function, so 0 to n, so 0, 1 to n. Okay, and this contain the exponents of polynomial constants. Okay, this contain the exponent of polynomials inequality constants. Okay, and what about your J transpose? So here your Gj is element of Rn. Here J is 1 to P because there are P number of equality constants. So this contain the exponents of the monomials equality constants of the original geometric program. Okay, so now if we change a variable, so your geometric problem is reduces to in this form. Okay, so now we define here the one transformation is here, and that transformation is the logarithmic transformation. So if we take the log of that, okay, so if you taking exponential of, if you're taking log of that, if you're taking log of that, you find this thing. Okay, and this is a linear one. This is your linear one. This is your affine function. Okay, and if we okay, not a fine function because here log of this is sum of some summation sign is already there. So this some sign, we take log of that, okay, the log of m, so this not equals to log of m plus log of n, because log of m into n equals to log of m plus log of n. But here we take the logarithmic function, we get log of this whole summation of that. And you know that log some exponential function, because this is a, if you taking log is there, log some exponential function is always convex function. Basically, if you taking log to both sides, so this objective function is log some exponential function, and you know that log some exponential function is convex function. And if we're taking log to side, it is log some exponential function. This is less equal to, we taking log here, is equal to 0 here. Okay, so this is a convex function, and your convex optimization problem, your objective function is convex, and your inequality function that less or equals to 0, that are also convex function, and your this equality function is affine function. If you're taking log of that, this is equal to simple linear function that equals to 0, and linear function is your affine function. If you're taking log to both, if you're taking two transformation, that is log Gaussian transformation, then this objective function is convex function, equality constant function is convex function, and your is affine function. So your this geometric programming problem is reduces to convex optimization problem. So if we're taking the transformation, that is log transformation, then the problem reduces to the convex optimization problem. So in next page, quickly write this thing. In next page, so now we transform the objective and constants constant functions by taking logarithmic by taking logarithm. So the results problem. So we can write minimize our objective function, and that objective function is some tilde here of variable because this is your new variable, and this equals to log of that k equals to 1 to k a to the power exponential of 0k y plus b0k. This is your objective function and subject to the constants. Constants are fi tilde y, and that is main function is log summation k equals to 1 to ki k transpose y plus exponential of plus bik. This is less or equals to 0, where I vary from 1 to m, and hj tilde, if you define this function, this is taking log of that, this is gj transpose plus hj, and that equals to 0, where j is 1 to p. Okay, so here you know that here your function, that is f tilde, here the function, since the function is fi tilde is convex. Convex क्यों? Because you know that log some exponential, always that function is convex functions. Okay, so this is convex, and as j, this is a affine function. This is affine, and this is convex for I equals to 0 to, because your objective function is also a convex function and equality constant function is also convex. These are convex, and this last one, equality one, is affine. So that's why you say that this problem is convex optimization problem. तो हम किसी भी प्रॉब्लम को, ज्योमेट्रिक प्रोग्रामिंग प्रॉब्लम को, बाय यूजिंग दिस ट्रांसफॉर्मेशन यू कैन प्रोड्यूस दैट प्रॉब्लम इज कॉन्वेक्स ऑप्टिमाइजेशन प्रॉब्लम, और हम से वैसे कॉन्वेक्स ऑप्टिमाइजेशन प्रॉब्लम सॉल्व करेंगे वैसे ही हम ज्योमेट्रिक प्रोग्रामिंग प्रॉब्लम्स को भी सॉल्व करेंगे. कैसे सॉल्व करनी सारी चीजें अब हम धीरे धीरे वहां पहुंच रहे हैं, कैसे हमें सॉल्व करना. ओके, तो आज इतना ही करते हैं. देन नेक्स्ट क्लास में हम फिर कुछ और डिस्कस करेंगे, और देखते हैं नेक्स्ट क्लास में हम कुछ न्यूमेरिकल ट्राई करेंगे कि वहाँ पे आपको बताएं, और या फिर हम थोड़ा ऑप्टिमाइजेशन प्रॉब्लम्स क्या होती है और मल्टी ऑपरेटिव प्रॉब्लम्स क्या होती हैं कल करा के फिर आपको न्यूमेरिकल पे ले चलेंगे. ठीक है, तो आज के लिए इतना ही. कल हम वेक्टर ऑप्टिमाइजेशन प्रॉब्लम वी विल डू सम न्यूमेरिकल ऑफ दैट. ओके, तो आज के लिए इतना ही.
थैंक यू सर.